Number 1, part A, show that the statement P implies P or not Q, and the statement P or Q and not P implies Q are equivalent. Show that these two statements are equivalent. In order to show two statements are equivalent, we have two choices. We can use formulas or we can use truth tables. Let me use formulas first. So if I use formula, I should show that left hand side equal to the right hand side. Left hand side is P implies P or not Q. If I use formula, P implies P or not Q can be rewritten as not P or P implies not Q. Because the statement P implies Q is equivalent to not P or Q. Here P represents P, the second part represents Q. So we have not P or Q. If I use a formula, I have not P or Q. Next, since an operation here is the same, we can apply associative law. So this statement can be rewritten as not P or P or not Q. Apply associative law. This statement can be rewritten as not P or P or not Q. And here, not P or P is always true. Not P or P is always true. Then we have true or not Q. And we know that the statement true or any statement is always true. True or any statement is always true. So here, true or not Q is true. So left hand side is always true. Next, we try to show that the right hand side get the same conclusion. For the right hand side, do the same thing. P or Q and not P implies Q. This statement can be rewritten as this statement P or Q and not P implies Q. It can be rewritten as not P or Q and not P or Q. For this statement, P implies Q is not P or Q. I treat the first part as P, treat the second part as Q. So I have not P or Q, not P or Q. Next, apply De Morgan's law. When you see a not in the front, apply De Morgan's law. It can be rewritten as not P or Q or not P or Q. Apply De Morgan's law. De Morgan's law says not P and Q is not P or not Q. When we distribute negation, operation in the middle change. Not P or Q become not P and not Q. When we distribute negation, operation in the middle will be switched. So when I distribute negation here, N become an O in the middle. The operation N become an O. Next, let's simplify this parenthesis. First part, not P or Q stays the same. For the second part, not P become P. And what's outside the parenthesis, or Q stays the same. Now here, consider we treat this as one statement. This is another statement. That's the third statement. Since operation here is the same, we can apply associative law. So this statement can be rewritten as not P or Q or P or Q. Consider this statement. P A or B or C. If we apply associative law, it can be rewritten as A or B or C. We treat this statement as A, treat this statement as B, this as C. So A or B or C can be rewritten as A or B or C. Put B and C together in the parentheses. A or B or C. Put B or C in the parentheses. Now observe here. we have not P or Q, or P or Q. This statement here looks exactly the same. So this statement here, consider the statement P or not P or P. Consider statement not P or P. This statement is always true. We can treat this as P. Treat this as not P or P. If we treat this as P, this statement is equivalent to not P or P, which is always true. Not P or P is always true. So left hand side equal to the right hand side. So left hand side is logically equivalent to the right hand side. In order to show that these two statements are equivalent, we can also use true tables. That's our second choice. So for true tables, let's observe find the variables. In this statement, we have two variables, P and Q. So in the table, put a variable in the first two columns. We have variables P and Q. Put the variables in the first two columns. Since there are two variables, we draw 4 rows for the true table. If there are 2 variables, draw 4 rows. If there are 3 variables, draw 8 rows for the true table, because 2 to the power 3 is 8. If there are 4 variables, it will be 16 rows in the true table, because 2 to the power 4 is 16. Then write down all possible outcomes for P and Q. So for P and Q, it could be both true. P is true, Q is false. P is false, Q is true, or they are both false. Write down all possible outcomes for the variables P and Q. Next, let's compute the first statement. In the first statement, we must do the premises first. And in the premises, we must compute not P, not Q first. So in the first statement, compute not Q first. Then once I know not Q, I can compute P or not Q. Then once I compute P or not Q, I compute P implies P or not Q. Then let's complete the table. When Q is true, not Q is false. When Q is false, not Q is true. When Q is true, not Q is false. When Q is false, not Q is true. Next, compute P or not Q. Compute P or not Q. Look at this column and this column. P or not Q, apply all. True or false is true. True or true is true. False or false is false. False or true is true. Next, compute P implies P or not Q. Look at the column of P and the column of P or not Q. Look at these two columns. Now for implication, keep the true table in mind. It's a little different. True implies true is true. True implies false is false. False implies true is true. False implies false is true. That's the true table for implication. So keep this table in mind. Here, look at these two columns. True implies true is true. True implies true is true. False implies false is true. False implies true is true. So the first statement is always true. Using the true table, we can see that the first statement is always true. Next, let's compute the second statement. Let's compute the true value for the second statement. Make table first. There are totally 2 variables, P and Q. Write P and Q in the first two columns. Then write down all possible outcomes for P and Q. They could be both true. P is true, Q is false. P is false, Q is true, or they are both false. In the second statement, we must compute the premises first. In the premises, we compute the inner premises first. So we compute P or Q, then compute not P. In the premises, we compute P or Q, then compute not P. Once I compute both premises, I compute the big premises. I compute P or Q and not P. P or Q and not P. Once I compute the entire premises, I compute the entire premises implies Q. So let's complete the table. P or Q, look at these two columns. True or true is true. True or false is true. False or true is true. False or false is false. Next we compute not P. When P is true, not P is false. When P is false, not P is true. Next we compute P or Q and not P. Look at these two columns here. P or Q and not P, apply N in the middle. True and false is false. True and false is false. True and true is true. False and true is false. Let's these big premises here. Next, compute the big premises implies Q. Look at this column and the column of Q. Read it this way. This statement comes first. False implies true. False implies true is true. Read it this way. False implies true. False implies true is true. False implies false. Read it this way. This statement comes first. Read it this way. False implies false. False implies false is true. True implies true. Read it this way. True implies true. True implies true is true. Last line. False implies false. False implies false is true. So you can see that the outcome of both statements in the true table is exactly the same. The outcomes in the true table for both statements, they are exactly the same. So they are equivalent. So P implies P or not Q is equivalent to P or Q and not P implies Q. So to show two statements are equivalent, we can use formulas or we can use true tables. Either way will give you the same conclusion. Number 1, part B. Show that the statement P and Q implies R and the statement P implies Q implies P implies R are equivalent. In order to show two statements are equivalent, we have two choices. We can either use formulas or we can use true tables. Let me first show you how to use formula to show that two statements are equivalent. So here, left hand side is P and Q implies R. If I use formula, this formula can be rewritten as not P and Q or R. If we treat this, the first part as P, second part as Q. P implies Q is equivalent to not P or Q. So P implies Q is not P or Q. Next, apply De Morgan's law. Not P and Q can be rewritten as not P or not Q. Apply De Morgan's law. Not P or not Q or R. And it looks like that's the best we can do for the statement on the left side. Next, let's try to simplify the right side, see if we can get the same thing. Right hand side is P implies Q implies P implies R. Let me rewrite the statement first. Consider this as the first part is P, second part is Q. P implies Q can be rewrite as not P or Q. If we treat the first part as P, second part as Q, P implies Q can be rewrite as not P or Q. So treat the first part as P, second part as Q. I get not P or Q. Next, rewrite the statement inside the parentheses. Inside the parentheses, P implies Q can be rewrite as not P or Q. For the second statement, rewrite what's inside the parentheses. P implies R can be rewrite as not P or R. Next, distribute not. Apply to Morgan's law. For the first part, apply to Morgan's law. Distribute not. If I distribute the negation, I have not P, which is P, and not Q. If I distribute negation, operation in the middle will be switched or become an N. Next, treat this as one statement. Treat this as A, this as B, this as C. We have A or B or C. A or B or C can be rewrite as A or B or C. If I treat this as A, this as B or C, because operation here is the same. I treat this as A, this as B, this as C. A or B or C can be rewrite as A or B or C. Treat this as A, this as B, this as C. So A or B or C can be rewrite as A or B or C. Next, apply distributive law. I can distribute not P into the parentheses. Distribute not P into the parentheses. I have P or not P. Distribute not P into the parentheses. I have P or not P. Not Q or not P. This operation go to the middle. N go to the middle. Or R stays the same. Then we know P or not P is always true. P or not P is always true. The second part stays the same. Not Q or not P. Then we have true and not P or not Q. We know the next statement says true and any statement P is the same as P. True and any statement P is the same as P. If we treat this as statement P, true and statement P is P. So here, true and this statement become the statement not Q or not P or R. Then observe the left side and right side is almost the same. If we apply commutative law, here, not Q or not P can be rewrite as not P or not Q. Then here we can see that left hand side and right hand side, they are exactly the same. So left hand side and right hand side are logically equivalent. So left hand side and right hand side, they are logically equivalent. In order to show that two statements are equivalent, we can also use truth table. Next, let me show you how to use truth table to show these two statements are equivalent. First of all, observe the statement. Find the variables here. In these two statements, we can see that the variables are P, Q, and R. There are three variables. So draw truth table, put P, Q, and R in the first three columns. if there are 3 variables in the true table, we need to draw 8 rows. Total power 3 is 8, so we need 8 rows from the true table. Then write down all possible outcomes for P, Q, and R. So let me show you a quick way to write down all possible outcomes. So for P, write 4 truths first, write 4 false. For Q, write 2 truths, 2 false, 2 truths, 2 false. And for R, write true, false, true, false, true, false, true, false. In the first statement, we need to compute P and Q first. Then take this parentheses implies R. Then compute the parentheses P and Q implies R. So for the first statement, we compute P and Q first. Then compute the parentheses P and Q implies R. So P and Q, look at P and Q here. True and true is true. True and true is true. True and false is false. True and false is false. False and true is false. False and true is false. False and false is false. False and false is false. Next, take P and Q implies R. Look at this column and this column. P and Q implies R. Read it this way. This statement comes first. True implies true. True implies false, and so on. Read it from right to left, because this statement must come first. So true implies true is true. Keep this table in mind. True implies true is true. True implies false is false. False implies true is true. False implies false is false. It's true. False implies false is true. False implies true is true. False implies false is true. False implies true is true. False implies false is true. So every row is true except the second row. Next, let's draw a table for the second statement. The setup is exactly the same. There are 3 variables. We draw 8 rows from the true table. Write down all possible outcomes for P, Q, and R, which is the same as the previous table. Then in the second statement, we must compute these 2 parentheses first. So first parenthesis is P implies Q. Second parenthesis is P implies R. After we compute these 2 parentheses, we compute P implies Q implies P implies R. Let's compute the first column here. P implies Q. True implies true is true. True implies true is true. True implies false is false. True implies false is false. False implies true is true. False implies true is true. False implies false is true. False implies false is true. Next, P implies R. Look at these 2 columns here. P implies R. True implies true is true. True implies false is false. True implies true is true. True implies false is false. False implies true is true. False implies false is true. False implies true is true. False implies false is true. Next, we compute the last column. Last column, we have P implies Q implies P implies R. Look at these 2 columns. P implies Q implies P implies R. Read it from left to right. This statement comes first, left to right. True implies true is true. True implies false is false. False implies true is true. False implies false is true. True implies true 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 is true. If we observe this column here, the outcome of both statements looks exactly the same. They have false in the second statement. They have false in the second row and true everywhere. They are exactly the same. So using true table, we can see that these two statements are equivalent. So P and Q implies R is equivalent to P implies Q implies P implies R. These two statements, they are equivalent since they have the same outcome in the true table. These two statements are equivalent. Number 2, determine the true value for each of the following statements. Assume the domain is the set of all integers. So part A, there is x such that x squared equal to 2x minus 1. If this statement is true for one of an x, then the statement itself is true. Is this statement true for one of an x? If I let s equal to 1, then x squared equal to 1 and 2x minus 1 also equal to 1. So x squared equal to 2x minus 1. So the statement is true when s equal to 1. Since the statement is true for one of an x, this statement is true. So part A is true. Part B, for all x greater than 1 implies x greater than 1. Is this statement true? If s squared greater than 1 implies s greater than 1 is true for all x, then the statement is true. But if it's false for one of an x, the statement will be false. Is this true for every x? Let's try. If I let x equal to -2, then x squared equal to 4, which is greater than 1. But x itself is not greater than 1. So x squared greater than 1 doesn't imply x greater than 1 for all x. So x squared greater than 1 doesn't apply x greater than 1. That's why this statement is false. Since it's not true for one of an x, the statement is false. Part C, for all x squared plus x is greater than or equal to 0. Is this statement true? If s squared plus x is greater than or equal to 0 for all x, then the statement will be true. But if s squared plus x is not greater than or equal to 0 for one of an x, the statement will be false. Let's try some x. If s is 0, 0 squared plus 0 is greater than or equal to 0. That's true. If s equal to 1, 1 squared plus 1 is 2. 2 is greater than 0. That looks true. If s is 2, 2 squared plus 2 is 6. 6 is greater than 0. That's true. Let's try some negative number. -1 squared plus -1 is 0. 0 is greater than or equal to 0. That's true. If s is -2, -2 squared is 4. X itself is -2. 4 plus -2 is 2. 2 is greater than 0. It's also true. It looks like the statement is true for all x. Let's try to prove it. It looks like this statement is true for all x. Let's try to prove it. Let's consider two cases. X, for any integer, s could be either greater or equal to 0, or s could be less or equal to -1. Consider two cases. S is greater or equal to 0, or s is less or equal to -1. Consider two cases. In the first case, if s is greater or equal to 0, then x squared is greater or equal to 0. So x squared plus x is greater or equal to 0. If s itself is greater or equal to 0, then s squared will be greater or equal to 0. So x squared plus x will be greater or equal to 0. So this statement is true when s is greater or equal to 0. If s is less or equal to -1, then then what happens? This statement x squared plus x can be rewritten as x times x plus 1. X squared plus x can be rewritten as x times x plus 1. If x is less than -1, then x plus 1 will be less or equal to 0. If x is less than -1, I add 1 to both sides. X plus 1 will be less or equal to 0. Then x squared plus x equal to x times x plus 1. X itself is negative. X plus 1 is also less or equal to 0. Negative number times the number less or equal to 0. Double negative is positive. X itself is negative. X plus 1 is also less or equal to 0. So x times x plus 1 double negative is positive. It's greater or equal to 0. So in both cases, we can see that here, x squared plus x is always greater or equal to 0. So the statement is true. Part D. There is x such that x equal to 1 minus x or 3x plus 1 equal to 0. If this statement here is true for 1 over x, the entire statement will be true. Otherwise, the statement is false. Can we find 1x that makes this statement true? Let's try. If we try to make the first statement true, then 2x must equal to 1, x must be half, which is impossible because we only consider domain to be integers. That's impossible. If we try to make the second statement true, s must be negative 1/3, which is also impossible because the domain is all integers. So it looks like we can make either of the statement true. So since this statement is not true for any x, the statement itself must be false. Since no x can make this statement true, then this statement must be false. So how do we prove it? We prove by contradiction. Assume there is a x such that assume there is an integer x such that x equal to 1 minus x or 3x plus 1 equal to 0. Then x must be half or negative 1/3. In both cases, x doesn't belong to integer. So this statement must be false. It's a contradiction. So this statement must be false. Number 2, part E. For all x, for all y, x squared plus y squared is always greater than or equal to 2sy. Is this statement here true for all x and y? By plugging in different numbers for x and y, it looks like the statement is always true. So we try to prove it. X squared plus y squared greater or equal to 2sy. This is equivalent to x squared minus 2sy plus y squared greater or equal to 0. And this statement is equivalent to x minus y squared greater or equal to 0. We know that perfect square is always greater or equal to 0. So this statement is always true. So prove it. For all x and y. For all integers x and y, because the domain for this problem, the domain is a set of all integers. For all x and y, for all integers x and y, x minus y squared is always greater or equal to 0. That means x squared minus 2sy plus y squared is always greater or equal to 0. That means x squared plus y squared is always greater or equal to 2sy. So the statement is true. This is our scratch work. Part F. For all x, there's a y such that 2x plus y is greater than 0. Here, can we find a y? Let's make 2x plus y greater than 0 for all x. This y, since it comes after x, it may depend on x. So, if I can make 2x plus y equal to 1, then the statement will be true. Then y will be 1 minus 2x. If I let y equal to 1 minus 2x, then this statement will be true. So, for all x, let y equal to 1 minus 2x. Since x is an integer, 1 minus 2 times the integer is also an integer. For all x, let y equal to 1 minus 2x. Then 2x plus y equal to 2x plus 1 minus 2x, which is equal to 1. 1 is greater than 0. So 2x plus y is greater than 0. This statement is true. For all x, I can find a y. Let's make this statement true. So this statement is true. And this is our scratch work. Part G. There is x such that for all y, x plus y squared is greater than 0. Is this statement true? Here, can we find one x which makes the statement true for all y? In this problem, x comes before y. So this x doesn't depend on y. So it must be a constant. So in this problem, can we find a constant x that makes the statement true for all y? We know that y squared is a perfect square. It must be greater or equal to 0. It must be non-negative. If I can let x be any positive number, then a positive number plus y squared will be strictly greater than 0. So this statement is true. Let's try to prove it. Let s equal to 1. Then for all integer y squared is greater or equal to 0. Then x plus y squared is greater or equal to 1 plus 0. X equal to 1. Y squared is greater or equal to 0. So x plus y squared is greater or equal to 1 plus 0, which is 1. And we know 1 is strictly greater than 0. So x plus y squared is greater or equal to 0, is strictly greater than 0. Since there's x, which makes the entire statement true for all y, that's why this statement is true. Number 2, part H. For all x, there's a y, such that y over x plus 2 is 1. Here, for every x, can we find a corresponding y, which makes this statement true? This y here may depend on x. It seems impossible. If I let x equal to negative 2, then we have y over 0. No matter what y is, it won't be 1. Even 0 over 0 is not 1. So this statement is false. To show the statement is false, we try to show that its negation is true. To show a statement is false, we try to show its negation is true. So negation of the statement is that there is x such that for all y over s plus 2 doesn't equal to 1. And we know that when s equal to negative 2, this statement is false. When s equal to negative 2, y over x plus 2 equal to y over 0, which doesn't equal to 1 for all y. So the negation of the statement is true. Since the negation of the statement is true, the statement itself is false. Since the negation of the statement is true, the statement itself is false. Part I. Let x such that for all y, s plus y over 2 equal to s cubed. Can we find x which makes this entire statement true? In this problem, since x comes before y, this x doesn't depend on y, so it must be a constant. So in this problem, can we find a constant x which makes this statement true? Here, since y comes after x, it's almost impossible to make this statement true. So if we try to show this statement is false, we try to show that the negation of this statement is false, is true. So let's write down the negation of the statement first. The negation of the statement says, for all x, there is a y, such that x plus y over 2 doesn't equal to s cubed. We try to prove the negation of the statement is true. So we try to make x plus y over 2 not equal to s cubed, which means, let's do some scratch work here. X plus y over 2 not equal to s cubed. That means x plus y doesn't equal to 2s cubed. If I subtract x from both sides, that means y doesn't equal to 2s cubed minus x. If I can make y equal to 2s cubed minus x plus 1, then y won't equal to 2s cubed minus x. Then this statement, x plus y over 2 won't be the same as s cubed. So let's prove the negation is true. For all integer x, let y equal to 2s cubed minus x plus 1. Since s is integer here, y is also integer. Then x plus y over 2 can be rewritten as x plus 2s cubed minus x plus 1 over 2. Let's s can cancel. We have 2s cubed plus 1 over 2. That equal to s cubed plus half. This is left side. And we know that s cubed plus half is strictly greater than s cubed. So x plus y over 2 won't be the same as s cubed. Since the negation of the statement is true, since here I prove that the negation of the statement is true, the statement itself must be false. Since here we prove that the negation of the statement is true, the statement itself must be false. Part J. For all x, for all y, x greater than y greater than 0 implies 1 over x is less than 1 over y. Is this statement true for all x and all y? Here, x is greater than y greater than 0. That means both s and y are positive. Since s is greater than y, the larger denominator for any fraction, if the numerator is the same, the larger denominator, the smaller it is. So it looks like the statement is true. Let's try to prove it. For all integers x and y, if x greater than y greater than 0, then both x and y are positive. Since x is greater than y, and they are both positive. Then the larger denominator, the smaller it is. So here it proves that the statement is true. Number 2, part K. For all x, there's a y, such that for all z, s plus y equal to z. Here, can we find integer y, which make this statement true for all x and all z? Also, since y comes after x, this y may depend on x, but y doesn't depend on z. This statement seems to be false because z comes after y. It seems to be false. So to show the statement is false, we try to show that the negation of a statement is true. Let me first of all write down the negation of a statement first. The negation of a statement says there is x such that for all y, there is a z such that x plus y doesn't equal to z. So if we try to make this statement x plus y not equal to z, I can simply let z equal to s plus y plus 1. Then z won't be the same as s plus y. So let's prove this statement is true. Let s equal to 0, which is an integer. Then for all integer y, let z equal to s plus y plus 1. But here s is 0, so z equal to 0 plus y plus 1. Z equal to y plus 1. Let z equal to y plus 1. Then the left hand side of the statement is x plus y, which is 0 plus y, that equal to y. And the right hand side of the statement is z equal to y plus 1. We can clearly see that left hand side is less than right hand side. So left hand side is less than right hand side. Hence, s plus y doesn't equal to z. So since the negation of the statement is true, the statement itself must be false. Since we prove the negation of the statement is true, the statement itself must be false. And this is our scratch work. We don't include this as part of the proof. Part L. For all x, for all y, there's a z such that 2x plus z equal to 3y plus 2z. Here, can we find an integer z which makes this statement true for all x and y? Here, z may depend on s and y. Since z comes after s and y, z may depend on s and y. If we try to make this statement true, we try to make 2s plus z equal to 3y plus 2z. Let's do some scratch work here. I can subtract z from both sides. This statement is equivalent to 2s equal to 3y plus z. Then I can bring 3y over. This statement is equivalent to 2x plus minus 3y. Equal to z. So if I let z equal to 2x minus 3y, this statement will be true. And z come after, since we have z come after x and y, I can write z in terms of s and y. So this statement seems to be true. So let's prove it. For all x and y, for all integers x and y, let z equal to 2x minus 3y. 2 times integer minus 3 times integer is also integer. So z is an integer. Left hand side of the statement is 2x plus z which is equal to 2x plus 2x minus 3y, that equal to 4x minus 3y. The right hand side of the statement is 3y plus 2z, which is 3y plus twice 2x minus 3y. It can be rewritten as 3y plus 4x minus 6y. If I combine like terms, I get 4x minus 3y. So we can see that left side equal to the right side. So left hand side equal to the right hand side. Hence 2x plus z equal to 3y plus 2z. Here we prove the statement itself is true. So this statement is true. And this part is our scratch work. We don't include it as a part of our proof. Number 2, part M. For all x, there's a y, there's a z, such that 1 over x equal to y over z. Can we find integers y and z that make this statement true? Here, y and z may depend on x. Since they both come after x, they may depend on x. If I let s equal to 0, then no matter what I choose for y and z, y over z won't be 1 over 0. So the statement is false. In order to show the statement is false, we try to show that the negation of the statement is true. So let me write down the negation of the statement first. The negation of the statement says there is x such that for all y, for all z, 1 over x doesn't equal to y over z. So, and we know that when s equal to 0, this statement 1 over 0 won't be the same as y over z. So let s equal to 0, which is an integer. Then 1 over x equal to 1 over 0, which is undefined. So for all y and z, for all integers y and z, 1 over x won't be the same as y over z. Since the negation of the statement is true, the statement itself must be false. Part N. There's x such that for all y, there's a z such that xz equal to y plus z. Can we find integers x and z which make this statement true? Here, x doesn't depend on y and z, it must be a constant. Z may depend on x and y, since it comes after x and y. Z may depend on x and y. Can we find integers x and z that make this statement true? So let's try some simple numbers. If I let s equal to 0, then I have 0 plus y. 0 equal to, if I let s equal to 0, then I have 0 equal to y plus z. And I can choose my z to be negative y. Then this statement will be true. So for all integer y, let z equal to negative y, which is also integer. Then we can see that the left hand side equal to xz, which is 0 times negative y equal to 0. The right hand side equal to y plus z, which is y plus negative y, which is also 0. So left hand side equal to right hand side. Hence xz equal to y plus z. So this statement is true. Since I can find x and z, which make the statement true, this statement is true. Number 3, part A. Let x be an integer. Show that if x plus 6 is odd, then 3x squared plus 7 is even. Proof. Since x is an integer, x could be either even or odd. Then either s is even or s is odd. If x is even, then s equal to 2k, where k must be an integer. So x plus 6 equal to 2k plus 6, which is 2 times k plus 3. Since k is an integer, k plus 3 is also integer. So x plus 6 is even, which is impossible because x plus 6 is odd. That's impossible. So x cannot be even. That means s must be odd. If s is odd, then s equal to 2k plus 1, where k is an integer. 3x plus 7, 3x squared plus 7 can be rewritten as 3 times 2k plus 1 square plus 7. Expand a perfect square. 2k plus 1 square can be rewritten as 4k square plus 4k plus 1. Distribute 3. We get 12k square plus 12k plus 3 plus 7. Combine like terms, I get 12k square plus 12k plus 10. Here I can pull out 2. If I pull out 2, I have 6k squared plus 6k plus 5. Since k is an integer, 6k squared plus 6k plus 5 must be an integer. So we have 3x squared plus 7 equal to 2 times integer. So 3x squared plus 7 must be even. Number 3, part B. Show that if s is odd, then a divides s squared minus 1. Let's prove it. Since x is odd, then s can be written as 2k plus 1, where k is an integer. Then x squared minus 1 can be written as 2k plus 1 square minus 1. Expand a perfect square. I have 4k square plus 4k plus 1 minus 1. Combine like terms. I get 4k square plus 4k. Here I can factor. I can pull out 4k. If I pull out 4k, I have 4k times k plus 1. Now, since k is an integer, then we have two cases. Integer k could be either even or odd. So two cases. Case 1, case even. Case 2, case odd. If k is even, then k can be written as 2 times n, where n is an integer. Then x squared minus 1 equal to 4 times 2n times k plus 1. That can be rewritten as a times n times k plus 1. Since n is an integer, k is an integer, so n times k plus 1 is an integer. So a divides x squared minus 1. That's case 1. When k is even, a divides x squared minus 1. Case 2, if k is odd, then k plus 1 is even. If k is odd, then k plus 1 must be even. So k plus 1 can be written as 2 times n, since k plus 1 is even. So k plus 1 equals 2 times n, where n is an integer. Then x squared minus 1 can be written as 4k times k plus 1, where k plus 1 is 2n. K plus 1 is 2n. That can be written as a times kn. Since both k and n are integers, k times n is an integer. Since x squared minus 1 equal to a times the integer, that means a divides x squared minus 1. So in both cases, we have a divides x squared minus 1. Therefore, a divides x squared minus 1. Number 3, part C. Show that if 1 over x is rational, then x squared plus x plus 1 over 2x is also rational. So let's prove it. Since 1 over x is rational, then by definition of rational number, 1 over x equal to 1 over b, where a and b are integers and b cannot be 0. The denominator b cannot be 0. Then if I cross multiply, b equal to ax. If I cross multiply, b equal to ax. Since b is not 0, then a cannot be 0 and x itself cannot be 0. Since b is not 0, both a and x cannot be 0. Next, we try to show this number x squared plus x plus 1 over 2x is rational. Here, since b equal to ax, then x equal to b over a. Then I can plug in x into this equation here. X squared plus x plus 1 over 2x. If I plug in, it can be rewritten as b over a squared plus b over a plus 1 over 2 times b over a. Here, the greatest common denominator is a squared. So I can multiply top and the bottom by a squared. It can be rewritten as b squared plus ab plus a squared over 2ab. Since a and b are integers, then the numerator a squared plus ab plus a squared, the numerator b squared plus ab plus a squared must be integers. And the denominator 2ab must also be integers. Since a is not 0, b is not 0, then the denominator 2ab cannot be 0. Since a is not 0, b is not 0, denominator 2ab cannot be 0. Since x squared plus x plus 1 over 2x can be written as an integer over integer, and the denominator is not 0, then we can say that x squared plus x plus 1 over 2x is rational. Number 3, show that half is not an integer. If we try to directly show that half is not an integer, it's not easy. A better way is try to prove this by contradiction. Proof by contradiction. Assume half is an integer. Let x equal to a half, then x must be an integer, and if I multiply both sides by 2, I have 2x equal to 1. Since 1 equal to 2 times the integer, since 1 equal to 2x, x is integer, then 1 must be even. The number 1 is even. That's a contradiction. We know number 1 is an odd number. Since 1 must be odd, so it's a contradiction. Once I find contradiction, that means the assumption must be wrong. So half is not an integer. Once I find contradiction, the assumption must be wrong. So half is not an integer. Number 3, part E. Let x and y be integers. Show that if 2xy plus 3y squared is even, then y must be even. For this problem, if we try to prove it directly, it's not easy to use the given information here. So for this problem, we can try to prove using contraposition. So proof using contraposition. Which means we assume the opposite of the conclusion. We try to prove the opposite of the hypothesis. So assume y is odd. Assume the opposite of the conclusion. Assume y is odd. We try to prove the opposite of the hypothesis. That means we try to prove 2xy plus 3y squared is odd. So assume y is odd. Then y can be written as 2k plus 1, where k is an integer. Then we try to prove 2xy plus 3y squared is even. So I plug in y into this equation. 2xy plus 3y squared, it can be rewritten as 2x times 2k plus 1 plus 3 times 2k plus 1 squared. Then let's multiply out. 2x times 2k plus 1. Let's multiply the perfect square first. 2k plus 1 squared is 4k squared plus 4k plus 1. Then distribute 2x and distribute 3. If I distribute 2x, I get 4xk plus 2x. If I distribute 3, I get 12k squared plus 12k plus 3. Since I try to show this number is odd, so I try to write this number as 2 times the integer plus 1. So I first of all rewrite number 3 as 2 plus 1. I rewrite 3 as 2 plus 1. Then for these terms here, I can factor 2 out. For every term in front of 1, I can factor 2 out. If I pull out 2, I have 2xk plus x plus 6k squared plus 6k plus 1 plus 1. Since both x and k are integers, since s is an integer, k is an integer, then this expression here must be an integer. So here I write 2xy plus 3y squared as 2 times the integer plus 1. so it must be odd. So 2xy plus 3y squared must be odd. So that's proved by contraposition. Number 3, part F. Show that if x is irrational, then 4x minus 1 is also irrational. For this problem, if we try to directly prove that 4x minus 1 is irrational, it's very hard. So here we can try to prove using contraposition. So proof using contraposition. We assume the opposite of the conclusion and try to prove the opposite of the hypothesis. So assume 4x minus 1 is rational. Then by its definition, by definition of rational number, 4x minus 1 can be written as a over b, where a and b are integers, and the denominator b cannot be 0. Next, we try to get x by itself. From this equation, we try to get x by itself and try to show that x is also rational. So from here, 4x minus 1 equal to a over b. If I multiply both sides by b, I can make 4bx minus b equal to a. Then I can add b to both sides. I get 4bx equal to a plus b. Next, I can divide both sides by 4b. S equal to a plus b over 4b. Since both a and b are integers, so a plus b must be integer. Same thing, since b is an integer, 4b must also be integer. Since b is not 0, then the denominator 4 times b is also not 0. Since b is not 0, 4 times b cannot be 0. Since s equal to integer over integer with denominator not equal to 0, then x must be a rational number. Since x is in the form of integer over integer with denominator not equal to 0, x must be a rational number. So that's the proof by contraposition. We assume the opposite of the conclusion. We prove the opposite of the hypothesis. That's proved by contraposition. Number 3, part G. Show that x cubed plus x plus 1 is not 0 for any integer x. To show x cubed plus x plus 1 is not 0, that's not easy. For this problem, we can try to prove by cases. Since x is an integer, x could be either even or odd. Case 1, x is even. If s is even, then s equal to 2k, where k is an integer. Then I can plug in k into this equation here. S cubed plus x plus 1 equal to 2k cubed plus 2k plus 1. Two k cubed can be rewritten as a k to the power 3, and 2k stays the same, number 1 stays the same. For the first two terms, I can pull out 2. If I pull out 2, I get 4k cubed plus k plus 1. Since k is an integer, 4k cubed plus k is also integer. So here, s cubed plus x plus 1 equal to 2 times the integer plus 1, it must be odd. So s cubed plus x plus 1, it must be odd. Hence, it cannot be 0. Hence, s cubed plus x plus 1 cannot be 0. That's case 1. Case 2, s could be even, s could be odd. Case 2, if s is odd, then s equal to 2k plus 1, where k is an integer. If s is odd, then s equal to 2k plus 1, where k is an integer. This expression, s cubed plus x plus 1, can be rewritten as 2k plus 1 cubed plus 2k plus 1 plus 1. If I expand the perfect cube, 2k plus 1 cube can be rewritten as ak cubed plus 12k squared plus 6k plus 1. And 2k plus 1 stays the same, plus 1. If I combine like terms, I can make ak cubed plus 12k squared plus 6k plus 2k is 8k. 1 plus 1 is 2. Leave the last one by itself. Then for the first 4 terms, I can pull out 2. If I factor 2 out, I have 4k cubed plus 6k squared plus 4k plus 1 plus 1. Since k is an integer, 4k cubed plus 6k squared plus 4k plus 1 must also be an integer. Since s cubed plus x plus 1 can be written as 2 times the integer plus 1, it must be an odd number. So s cubed plus x plus 1 must be odd. Hence, it cannot be 0. Since this number is odd, it cannot be 0. So in both cases, we get the same conclusion. Therefore, s cubed plus x plus 1 cannot be 0. That's the proof. Number 3, part H. Let x and y be integers. Show that if the GCD of x and y is 1, then the expression xy plus 3x plus 5y must be odd. For this problem, we can try to prove by cases. We know in general for integers, integer could be either even or odd. If there are 2 integers, it will be 4 cases. They are either s and y, they are both even, both odd, or s is even, y is odd, or s is odd, y is even. There are 4 cases. But for this problem, since the GCD of sy is 1, then s and y they cannot be both even. If they are both even, the GCD of s and y must be at least 2. So since GCD of s and y is 1, the s and y cannot be both even. So we have 3 cases. Since the GCD of x and y is 1, then x and y cannot be both even. S and y can be both even. So there are 3 cases. Case 1, x and y, they are both odd. Case 2, x is odd, y is even. Case 3, x is even, y is odd. There are 3 cases. If x and y they are both odd, then s equal to 2k plus 1. and y equal to 2l plus 1, where k and l are integers. So the expression xy plus 3x plus 5y, it can be written as 2k plus 1 times 2l plus 1 plus 3 times 2k plus 1 plus 5 times 2l plus 1. Then multiply out. If I multiply 2k plus 1 times 2l plus 1, I get 4kl plus 2k plus 2l plus 1 plus 6k plus 3 plus 10l plus 5. Then combine like terms. I have 4kl plus 2k plus 6k is 8k. 2l plus 10l is 12l. 1 plus 3 plus 5 is 9. 9 can be written as 8 plus 1. Then for the first 4 terms, I can factor 2 out. If I factor 2 out, I get 2 times 2kl plus 4k plus 6l plus 4 plus 1. Since both k and l are integers, so this expression 2kl plus 4k plus 6l plus 4 must be integer. Now, since the expression xy plus 3x plus 5y can be written as 2 times the integer plus 1, this must be an odd number. So xy plus 3x plus 5y must be odd. That's case 1. In the first case, if x and y are both odd, we show that xy plus 3x plus 5y is odd. Case 2. X is odd and y is even. Case 2, x is odd and y is even. If x is odd, then x can be written as 2k plus 1. If y is even, then y can be written as 2l, where k and l are integers. Again, now we plug in k and l into this expression here. Sy plus 3x plus 5y. If I plug in k and l, I have 2k plus 1 times 2l plus 3 times 2k plus 1 plus 5 times 2l. Then multiply everything out. I have 4kl plus 2l plus 6k plus 3 plus 10l. Then combine like terms. I have 4kl plus 12l plus 6k. Number 3 can be written as 2 plus 1. Next, for the first 4 terms, I can factor 2 out. If I factor 2 out, I get 2 times 2kl plus 6l plus 3k plus 1 plus 1. Since both k and l are integers, then 2kl plus 6l plus 3k plus 1 must be an integer. So, since xy plus 3x plus 5y equal to 2 times the integer plus 1, it must be an odd number. That's case 2. In case 2, we also prove that xy plus 3x plus 5y is odd. Next, case 3. Case 3, x is even, y is odd. If x is even, y is odd, then x can be written as 2 times k. And y can be written as 2l plus 1, where k and l, they are both integers. So next, we plug in x and y into the expression xy plus 3x plus 5y. Next, we plug in sy into this expression. X is 2k, y is 2l plus 1, plus 3 times x is 2k, plus 5 times y is 2l plus 1. Next, we can distribute and combine like terms. If I distribute 2k, I get 4kl plus 2k. 3 times 2k is 6k. Distribute 5, I get 10l plus 5. Combine like terms, I get 4kl plus 2k plus 6k is 8k plus 10l. Number 5 can be rewritten as 4 plus 1. Then for the first 4 terms, I can factor 2 out. It can be rewritten as 2 times 2kl plus 4k plus 5l plus 2 plus 1. Since both k and l are integers, then 2kl plus 4k plus 5l plus 2 must be an integer. Since sy plus 3x plus 5y can be written as 2 times the integer plus 1, it must be odd. So sy plus 3x plus 5y is odd. Since in all 3 cases we get the same conclusion, so xy plus 3x plus 5y must be odd. That's the proof. Number 3, part I. Let x be an integer. Show that if 5 divides x minus 2, then 5 divides x cubed plus 2. For this problem, we can try to prove it directly. Since 5 divides x minus 2, that means 5 times an integer k equal to x minus 2, where k is an integer. That's the definition of divisibility. If 5 divides x minus 2, that means 5 times the integer k equal to x minus 2. Here, k is an integer. Then, in this equation, 5k equal to x minus 2. If I solve an equation for x can be rewritten as 5k plus 2. Next, we try to compute x cubed plus 2. X cubed plus 2 can be rewritten as 5k plus 2 cubed plus 2. For 5k plus 2 cubed, if I expand the perfect cube, I get 125k cubed plus 150k squared plus 60k plus a plus 2. If I combine like terms, I get 125k cubed plus 150k squared plus 60k plus 10. We try to show that 5 divides this number, so I can try to factor 5 out. If I factor 5 out, I get 25k cubed plus 30k squared plus 12k plus 2. Since k is an integer, this expression 25k cubed plus 30k squared plus 12k plus 2 must also be an integer. Since x cubed plus 2 can be written as 5 times the integer, that means 5 divides x cubed plus 2. That's the proof. Number 4, prove or disprove each of the following statements. Part A, for any integer x, if 4x squared plus 1 is odd, then 3x plus 1 is also odd. We try to prove or disprove this statement. If this statement is true, we prove it. If this statement is false, we try to find a counterexample to disprove this statement. So, is this statement true for all x? Let's try to plug in some value, see if this statement is always true. Here, if s is 0, 4x squared plus 1 is 0 plus 1, which is 1, and 1 is odd, that's true. The conclusion here, 3 times 0 plus 1 is also 1. 1 is odd, that's also true. True implies true is true. So when s is 1, this statement is true. How about s equal to 1? When s is 0, this statement is true. How about s equal to 1? When s equal to 1, 4 times 1 squared plus 1, that's 5. 5 is odd, that's true. When s is 1, 3 times 1 plus 1 is 4. 4 is odd, that's false. And we know that true implies false is false. So this statement is not true when s equal to 1. That's a counterexample. That's a counterexample. So this statement is false. We try to disprove it using a counterexample. This statement is false. It's a false statement. Let's disprove it. Let x equal to 1. Then 4x plus 1 equal to 4 plus 1, which is equal to 5, which is odd. But 3x plus 1 equal to 3 plus 1 equal to 4, which is even. So this statement is not true. We disprove it using a counterexample. Number 4, part B. If 2x plus 3y minus 1 is irrational, then either x is irrational or y is irrational. We try to prove or disprove this statement. First of all, let's decide, is this statement true or false? Let's first of all try to find some examples. Can we find any example that make a hypothesis true, but the conclusion false? We can try some examples. It seems impossible to make a hypothesis true, but the conclusion false. So this statement, it looks like it's a true statement. Let's try to prove it. For this statement, we can try to prove using contradiction. Direct proof is too hard to prove s or y is either s is irrational or y is irrational. Direct proof is too hard. So let's try to prove by contradiction. So assume the opposite of the conclusion. Here the conclusion says either s is irrational or y is irrational. The conclusion is in the form of P or Q. The opposite of this statement, the opposite of conclusion, by De Morgan's law, it can be written as not P, N, not Q. So all become N. That means the opposite of conclusion is x is rational, and y is rational. So the opposite of the conclusion says x is rational and y is rational. Then, by definition of rational number, x can be written as a over b, and y can be written as c over d, where a, b, c, d are integers, and the denominator b and d cannot be 0. That's the definition of rational number. Next, we try to prove that 2x plus 3y minus 1 is rational. We try to prove an opposite of an hypothesis. So here, 2x plus 3y minus 1 can be written as 2 times a minus b plus 3 times c over d, 2 times a over b plus 3 times c over d plus 1. It can be rewritten as 2a over b plus 3c over d plus 1. For these three terms, we try to find the least common denominator. Here, the least common denominator is b times d. So, for the first term, I multiply top and bottom by d. I get 2ad. For the second term, I can multiply top and bottom by b. I get 3bc. And for the last term, I write 1 as 1 over 1. Multiply top and bottom by b times d. I get bd. The common denominator is bd. Since a, b, c, d are integers, then 2ad plus 3bc plus bd must be integers. Same thing, since d is an integer, since b and d are integers, b times d must also be integer. And since b is not 0, and d is not 0, then the denominator b times d cannot be 0. Since b is not 0, d is not 0, the denominator b times d cannot be 0. Then, since 2x plus 3y minus 1 equal to an integer over an integer, where the denominator is not 0, then 2x plus 3y minus 1, it must be rational. That's an opposite of the hypothesis. So let's prove by contradiction. This is a true statement. We prove it by contradiction. Number 4, part C. Prove or disprove that if both x and y are irrational, then 2x squared plus y is irrational. We need to first of all determine whether this statement is true or false. So let's try some examples. If we can find an example that makes the hypothesis true, but the conclusion false, then this is a false statement. We can use a counterexample to disprove it. Otherwise, this is a true statement, we have to prove it. So, let's try some examples. If I let x equal to, say, 2, to the fourth root of 2, let y equal to negative 2 square root of 2, then they are both irrational. They are both irrational. The hypothesis is true. How about 2x squared plus y? 2x squared plus y is 2 times 2 to the fourth root square plus y. That's 2 square root of 2 plus negative 2 square root of 2, which is 0. 0 is rational, so the conclusion is false. Here we find an example that makes the hypothesis true, but the conclusion false. So this statement is false. So to disprove this false statement, we give a counterexample. And this is a counterexample. Here we know that it's a false statement. To disprove it, we give a counterexample. Let s equal to the fourth root of 2 and y equal to negative 2 square root of 2. then we know that both x and y are irrational. Then both x and y are irrational. But 2x squared plus y equal to 2 times the fourth root of 2 squared plus negative 2 radical 2. That can be written as 2 radical 2 minus 2 radical 2, which is 0. So 2x squared plus y equal to 0 is rational. Since this example makes the hypothesis true, conclusion false, this is a counterexample to disprove this statement. Number 4, part D. Prove or disprove that for any integers a, b, c, if a divides b, c, then either a divides b or a divides c. First of all, we need to determine whether this statement is true or false. Let's try to find some example. If we can find an example that makes the hypothesis true, but the conclusion false, then this is a false statement. We can give a counterexample to disprove it. Otherwise, this is a true statement. We have to prove it. So let's try some examples first. Let's pick some value for a, b, and c. We try to make the hypothesis true, but the conclusion false. If I let a equal to 4, b equal to 2, c equal to 6, then we know that b times c is 12. A divides b, c, because 4 divides 12. But a doesn't divide b, because 4 doesn't divide 2. And a doesn't divide c, because 4 doesn't divide 6. So that's a counterexample. If we can find a counterexample, this is a false statement. We can disprove this statement using a counterexample. This is a counterexample. Let me write it over. This is a counterexample. Let me write it over. So we disprove this statement using a counterexample. Let integers a equal to 4, b equal to 2, c equal to 6, then b times c equal to 12. Since 4 divides 12, then we know that a divides bc. But 4 doesn't divide 2, and 4 doesn't divide 6. Then we know that a doesn't divide b, and a doesn't divide c. So that's an example that makes the hypothesis true, but the conclusion false. This is a counterexample to disprove this statement. Number 5. Prove each of the following statements using mathematical inductions. Part A. Show that half plus 1/4 plus 1/8 plus 1 over 2 to the power n equal to 1 minus 1 over 2 to the power n for all positive integer n. So we try to use mathematical induction to prove this statement. First of all, I suggest you rewrite the left side in sigma notation first. To make the problem a little easier, rewrite the left side in sigma notation first. First term is 1 over 2. Second term 1 over 4 can be rewrite as 1 over 2 squared. The third term is 1 over 2 to the power 3. The last term is 1 over 2 to the power n, which can be rewritten as the sigma n I from 1 to n. One over 2 to the power I. So when I is 1, I get 1 over 2. When I is 2, I get 1 over 2 squared. When I is 3, I get 1 over 2 to the power 3. The last term, when I is n, I get 1 over 2 to the power n. So I can rewrite, to make the problem a little easier, rewrite the left side in sigma notation. Then let's try to prove this statement using mathematical induction. For mathematical induction, we first want to verify that the statement is true for the first n. That's called a basis step. Basis step. Verify that the statement is true for the first n. Here n is the set of all positive integers. So the first n is n equal to 1. When n equal to 1, left hand side is the sigma notation I from 1 to 1, because n is 1. So I is from 1 to 1. 1 over 2 to the power I. Since I is from 1 to 1, we plug in 1 for I. I get 1 over 2 to the power 1, which is a half. That's left hand side. Right hand side here, I plug in 1 for n. I get 1 minus 1 over 2 to the power 1. 1 minus a half is a half. So we have left hand side equal to the right hand side. We verify that this statement is true for the first n. This statement is true for the first n. Next, it's called inductive step. We assume this statement is true when n equal to k. We try to prove that this statement is also true when n equal to k plus 1. When n equal to k, we assume this statement is true when n equal to k. So 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 2 to the power k equal to 1 minus 1 over 2 to the power k. Assume this statement is true when n equal to k. This is called the induction hypothesis. This statement here is called the induction hypothesis. We try to prove this statement is also true when n equal to k plus 1. When n equal to k plus 1, left hand side equal to the summation I from 1 to k plus 1. When n equal to k plus 1, we plug in k plus 1 for n. 1 over 2 to the power I. That's the left hand side. That equal to 1 over 2 plus 1 over 4 plus 1 over 8. Here I varies from 1 to k plus 1. So eventually I will reach k. Then I will eventually reach k plus 1. So that's the term that I equal to k. And that's the last term, I equal to k plus 1. That's the left hand side. And we know that by induction hypothesis, the sum 1 half 1 over 4, 1 over 8 to 1 over 2 to the power k, this equal to 1 minus 1 over 2 to the power k by induction hypothesis. That equal to 1 minus 1 over 2 to the power k. That's by the induction hypothesis. Last term stays the same, 1 over 2 to the power of k plus 1. Then it can be rewritten as 1 minus 1 over 2 to the power k plus 1 over 2 to the power of k plus 1. Next, we should combine these two fractions together. I can find the common denominator first. The common denominator is 2 to the power of k plus 1. So for the second term, I can multiply the top and the bottom by 2. If I multiply the top and the bottom by 2, I get 1 minus 2 over 2 to the power of k plus 1 plus 1 over 2 to the power of k plus 1. that equal to 1 minus 1 over 2 to the power of k plus 1. If I combine like terms, negative 2 plus 1 is negative 1. And that's the same as the right hand side if I plug in k plus 1 for n. This is the same as the right hand side if I plug in k plus 1 for n. So that equal to the right hand side. That complete proof by induction. We first of all verify that the statement is true for the first n. Then we assume the statement is true for when n equal to k. We prove that the statement is also true for n equal to k plus 1. That's a proof by mathematical induction. Number 5, part B. Show that 2 to the power 3 plus 4 to the power 3 plus 6 to the power 3 plus plus 2n to the power 3 equal to 2 to the n squared times n plus 1 squared for all positive integer n. We try to prove this using mathematical induction. So first of all, I can try to rewrite the left side in sigma notation first. I can first of all rewrite the left side in sigma notation first. First term is 2, second term is 4. 4 can be rewritten as 2 times 2. 6 can be rewritten as 2 times 3. So this can be rewritten as I from 1 to n, 2i to the power 3. When I is 1, 2 times 1 is 2. When I is 2, 2 times 2 is 4. When I is 3, 2 times 3 is 6. And when I is n, for the last term, when I is n, 2 times n is 2n. So I can rewrite the left side in sigma notation first. Next, proof by induction. We first of all verify that this statement is true for the first n. We first of all verify that this statement is true for the first n. That's the basis step. Since n represents all positive integers, so the first n is number 1. If I plug in 1, left hand side is the summation I from 1 to 1. I plug in 1 for n. 2i to the power 3. When I is 1, I have 2 times 1 to the power 3, which is a. For the right hand side, do the same thing. I plug in 1 for each n. I get 2 times 1 squared times 1 plus 1 squared. 2 times 1 squared is 2. 1 plus 1 squared is 4. 2 times 4 is a. So here, left side equal to the right side. Left hand side equal to the right hand side. So here we prove that left hand side equal to the right hand side. So this statement is true when n equal to 1. Next, the inductive step. We assume the statement is true when n equal to k. We try to prove that the statement is also true when n equal to k plus 1. So we assume for inductive step, when n equal to k, we assume the statement is true when n equal to k. We assume 2 to the power 3 plus 4 to the power 3 plus 6 to the power 3 plus 2k to the power 3 equal to 2k squared times k plus 1 squared. Assume this statement is true when n equal to k. We try to prove that the statement is also true when n equal to k plus 1. This statement here is the induction hypothesis. This assumption is called the induction hypothesis. Now, we try to prove the statement is also true when n equal to k plus 1. When n equal to k plus 1, from the left hand side, we plug in k plus 1 for this n. Left hand side is the summation I from 1 to n. Here n is k plus 1. 2i cubed. If I expand this sigma notation, first term, if I plug in 1, I get 2 to the power 3. For the second term, if I plug in 2, I get 4 to the power 3. For the third term, if I plug in 3, I get 8 to the power 3. get 6 to the power 3. Then the last term, I equal to k plus 1. The second last term, I will be k. When I is k, I get 2k to the power 3. The last term will be 2 times k plus 1 to the power 3. That's the term I equal to k plus 1. And that's the term I equal to k. I is from 1 to 3, eventually reach k, then k plus 1. That's the term I equal to k. That's the term I equal to k plus 1. By induction hypothesis, 2 cube plus 4 cube plus 6 cube plus 2k cube, that equal to 2k squared times k plus 1 squared. This is the induction hypothesis. And the last term here is 2 times k plus 1 cube. Let's simplify this expression first. It looks too complicated. Let's simplify first. First part, I first of all leave it the same. I get 2k squared times k plus 1 squared. Leave it the same. For the second part, I distribute perfect cube first. 2 cube is 8. K plus 1 cube, I first of all leave it the same. Now observe the first part and the second part. We see that here, k plus 1 is a common factor. And the lower power is power 2. I can pull out k plus 1 squared. And number 2 is also a common factor. I can also pull out number 2. So common factor here is 2 times k plus 1 squared. If I pull out 2 times k plus 1 squared, in the first term, what's left is k squared. In the second term, what's left is 4 times k plus 1. Then distribute 4 and combine like terms. I get 2 times k plus 1 squared times k squared plus 4k plus 4. Then factor the second part. K squared plus 4k plus 4 can be rewritten as k plus 2 squared. That's the left hand side. Now for the right hand side, when n equal to k plus 1, I plug in k plus 1 for each n. I have 2 times k plus 1 squared, k plus 1 plus 1 squared. That can be rewritten as 2 times k plus 1 squared, and k plus 1 is k plus 2 squared. So here we see that left hand side and right hand side, they are exactly the same. So left hand side equal to the right hand side. That means this statement is also true when n equal to k plus 1. So let's complete the induction, the proof by induction. Let's complete the proof by mathematical induction. Number 5, part C. Show that 2 to the power n is greater than or equal to n cubed plus n for all integer n greater than or equal to 10. So we try to prove this statement by mathematical induction. First of all, we try to verify that the statement is true for the first n value. Here, n represents integers greater than or equal to 10. So the first n value is n equal to 10. So the basis step. Verify that the statement is true when n equal to 10. When n equal to 10, left hand side is 2 to the power 10. 2 to the power 10 is 1024. Right hand side is 2 to the power 10 to the power 3 plus 10. 10 to the power 3 is 1000. 1000 plus 10 is 1010. So you can see that left hand side is greater than or equal to right hand side. So here we see that left hand side is greater than or equal to right hand side. This statement is true when n equal to 10. Next, inductive step. First of all, assume the statement is true when n equal to k. We try to prove that the statement is also true when n equal to k plus 1. when n equal to k, we assume this statement is true when n equal to k. We assume 2 to the power k is greater or equal to k to the power 3 plus k. Here k could be any integer greater or equal to 10. Assume this statement is true when n equal to k. We try to prove that the statement is also true when n equal to k plus 1. When n equal to k plus 1, left hand side is 2 to the power of k plus 1. Right hand side is k plus 1 cube plus k plus 1. We try to prove that left hand side is greater than or equal to the right hand side, or right hand side is less than or equal to the left hand side. Either show that left side is greater or equal to right hand side, or right hand side is less or equal to left hand side, whichever is easier. In this case, right hand side looks more complicated, so I will start from right hand side. I try to show that right hand side is less than or equal to the left hand side. So since right hand side looks more complicated, I start from right hand side. Here, right hand side is k plus 1 cube plus k plus 1. If I expand the perfect cube, I get k cube plus 3k squared plus 3k plus 1. And k plus 1 stays the same. Next, I can combine like terms. If I combine like terms, I get k cube plus 3k squared plus 4k plus 2. Then we try to make this expression a little simpler. This is less than k cube plus 3k squared plus 4k squared plus 2k squared. Here I leave the first term the same, leave the second term the same. For the third term, k is less or equal to k squared, because k is greater than 10. So k by itself is less or equal to k squared, and 2 by itself is less or equal to 2k squared. So this expression, k cubed plus 3k squared plus 4k plus 2, is less than k cubed plus 3k squared plus 4k squared plus 2k squared. Then if I combine like terms, this expression equal to k cubed plus 9k squared. If I combine like terms, 3k squared plus 4k squared plus 2k squared is 9k squared. Since k is an integer greater or equal to 10, then we know that 9 is less than 10, 10 is less or equal to k, so 9 is less than k. So this expression is less or equal to k cubed plus k times k squared, because 9 is less or equal to k. So 9k squared is less or equal to k times k squared. That equal to 2k cubed. If I simplify, this equal to 2k cubed. Next, we try to use the induction hypothesis. This assumption here is the induction hypothesis. Next, we try to use the induction hypothesis here. 2k cubed. K cubed by itself is less than k cubed plus k. K cubed by itself is less than k cubed plus k, because k is greater or equal to 10. Then, by induction hypothesis, k cubed plus k is less or equal to 2 to the power k. 2 to the power k is 2 to the power of k plus 1. That's the left hand side. So here we prove that the right hand side is less than or equal to the left hand side. Let's complete the proof by induction. Number 5, part D. Show that n factorial is greater than or equal to 3 to the power n plus n for all integer n greater than or equal to 7. We try to prove this problem by mathematical induction. For proof by induction, we first of all try to verify that this statement is true for the first n. Here, n represents integers greater than or equal to 7. So the first n is n equal to 7. So first of all, the basic step, we try to prove that this statement is true when n equal to 7. When n equal to 7, left hand side is 7 factorial. 7 factorial is 5040. For the right hand side, I plug in 7 for n. I get 3 to the power 7 plus 7. 3 to the power 7 is 2187. Plus 7, that's 2194. So here we can see that left hand side is greater than right hand side. So when n equal to 7, this statement is true. Left hand side is greater than or equal to the right hand side. The statement is true. This statement is true when n equal to 7. Next, the inductive step. For the inductive step, we assume this statement is true when n equal to k. We try to prove that this statement is also true when n equal to k plus 1. So when n equal to k, we assume this statement is true for k. So assume k factorial is greater or equal to 3 to the power k plus k, where k is an integer greater or equal to 7. That's an assumption. This is called induction hypothesis. We try to use the induction hypothesis to prove that this statement is also true when n equal to k plus 1. When n equal to k plus 1, left hand side is k plus 1 factorial. Right hand side is 3 to the power of k plus 1 plus k plus 1. We need to show that left hand side is greater than or equal to the right hand side, or we can also show that right hand side is less than or equal to the left hand side. Either way is okay, but in this problem, the right hand side looks more complicated, so we can start from the right hand side. Try to show that right hand side is less than or equal to the left hand side. So this problem, right hand side is 3 to the power of k plus 1 plus k plus 1. It can be rewritten as 3 times 3 to the power k plus k plus 1. We know that since 7 is greater or equal to k, then number 1 is less than 2k. Since k is greater or equal to 7, number 1 is less than 2k, less than or equal to 2k. So we have 3 times 3 to the power k plus 3k. Here I can factor 3 out. If I factor 3 out, I get 3 to the power k plus k. And we know that 3 to the power k plus k is less than or equal to k factorial. That's by induction hypothesis. 3 to the power k plus k is less than k factorial. And also, since k is greater than 7, that means 3 is less than k, so 3 is less than k. 3 is less than 7, 7 is less than k, so 3 is less than k. And also, k is less than k plus 1. Since 3 is less than 7, 7 is less or equal to k, k is less than k plus 1, 3 is less than k plus 1. And we know that k plus 1 times k factorial is k plus 1 factorial. This is the left hand side. So here we see that right hand side is less or equal to the left hand side. Let's complete the proof by induction. Since we show that the right hand side is less than left hand side, when n equal to k plus 1, we complete the proof by induction. Number 5, part E, show that 7 divides a to the power m minus 1 for all integer n greater than or equal to 0. For this problem, we try to prove it by mathematical induction. So first of all, we try to verify that this statement is true for the first n. Here, n represents integers greater than or equal to 0. So the first n value is n equal to 0. So for basic step, we try to verify that this statement is true when n equal to 0. When n equal to 0, a to the power m minus 1 is a to the power 0 minus 1, which is 1 minus 1 equal to 0. Since 7 divides 0, then we can say that 7 divides am minus 1 when n equal to 0. So this statement is true when n equal to 0. That's the basic step. Next, for the inductive step, we assume that this statement is true when n equal to k, and use it to prove that the statement is also true when n equal to k plus 1. So when n equal to k, assume 7 divides a to the power of k minus 1. We try to use it to prove that this statement is also true when n equal to k plus 1. 7 divides a to the power k minus 1. That means 7 times the integer m equal to a to the power k minus 1. That means a to the power k can be rewritten as 7m plus 1, where m is an integer. A to the power k equal to 7m plus 1. This is our induction hypothesis. We try to use it to prove that this statement is also true when n equal to k plus 1. When n equal to k plus 1, a to the power m minus 1, that equal to a to the power of k plus 1 minus 1. A to the power of k plus 1 can be rewritten as a to the power k times a minus 1. And a to the power k is 7m plus 1. Then distribute number a, I get 56m plus a minus 1. If I combine like terms, I get 56m plus 7. We try to show that am minus 1 is divisible by 7. So here I can try to factor 7 out. If I pull out 7, I get am plus 1. Since m is an integer, then am plus 1 is also an integer. Since am minus 1, a to the power m minus 1 equal to 7 times the integer, that means 7 divides am minus 1 when a equal to k plus 1. 7 divides am minus 1 when n equal to k plus 1. That complete the proof by mathematical induction. Number 5, part F. Show that 5 divides 2 to the power of 3n plus 4 plus 3 to the power of n plus 2 for integer n greater than or equal to 0. We try to prove this statement using mathematical induction. So proof by induction. We first of all try to verify that this statement is true for the first n. Here n represents integers greater than or equal to 0. So the first n value is n equal to 0. So here for the basic step, we try to verify that this statement is true when n equal to 0. When n equal to 0, 2 to the power of 3m plus 4 plus 3 to the power of m plus 2, that can be rewritten as 2 to the power of 4 plus 3 to the power of 2. 2 to the power 4 is 16, 3 to the power 2 is 9, 16 plus 9 is 25. So since 5 divides 25, then we can say 5 divides 2 to the power of 3m plus 4 plus 3 to the power of m plus 2 when a equal to 0. That's the basis step. We show that this statement is true when a equal to 0. Next, for inductive step, we assume that this statement is true when n equal to k, and we try to use it to prove that this statement is also true when n equal to k plus 1. When n equal to k, we assume this statement is true when n equal to k. So assume 5 divides 2 to the power of 3k plus 4 plus 3 to the power of k plus 2. We try to use it to prove that this statement is also true when n equal to k plus 1. Let me rewrite this statement first. 5 divides 2 to the power of 3k plus 4 plus 3 to the power of k plus 2. That means 5 times the integer m equal to 2 to the power of 3k plus 4 plus 3 to the power of k plus 2, where m is an integer. For these two terms, the first term looks more complicated, so I try to get the first term by itself. That means 2 to the power of 3k plus 4 equal to 5m minus 3 to the power of k plus 2. This is the induction hypothesis. We try to use it to prove that this statement is also true when n equal to k plus 1. When n equal to k plus 1, 2 to the power of 3m plus 4 plus 3 to the power of m plus 2, it can be rewritten as 2 to the power of 3 times k plus 1 plus 4 plus 3 to the power of k plus 1 plus 2. Since we try to use the induction hypothesis, so in the exponent, we try to get 3k plus 4 by itself and k plus 2 by itself. For the first term, it can be rewritten as 2 to the power of 3k plus 4 plus 3. I distribute 3, then move 4 to the front. Second part, I can write this as k plus 2, 3 to the power of k plus 2 plus 1. I switch 1 and 2. Then the first term can be rewritten as 2 to the power of 3k plus 4 times 2 to the power of 3. Second term can be rewritten as 3 to the power of k plus 2 times 3 to the power of 1. Then substitute. I can replace 2 to the power of 3k plus 4 with 5m minus 3 to the power of k plus 2. Times 2 to the power of 3. 2 to the power of 3 is a. Second term can be rewritten as 3 to the power of k plus 2 times 3. 3 to the power of 1 is 3. Then in the first part, I can distribute a. If I distribute a, I get 40m minus a times 3 to the power of k plus 2. Second, the last part can be rewritten as 3 times 3 to the power of k plus 2. Then here I can combine like terms. Negative a plus 3 is negative 5. So I get 40m minus 5 times 3 to the power of k plus 2. I combine like terms. Negative a plus positive 3 is negative 5. We try to show that number 5 divides 2 to the power of 3k plus 4 plus 3 to the power of k plus 2. We try to show number 5 divides this number. So here I can try to factor 5 out. If I factor 5 out, I get am minus 3 to the power of k plus 2. Since m is an integer, k is also integer, then am minus 3 to the power of k plus 2 is an integer. Since this number equal to 5 times the integer, that means 5 divides 2 to the power of 3m plus 4 plus 3 to the power of m plus 2. When n equal to k plus 1. That complete the proof by mathematical induction.